The topic for today is, as you can see, shearing stress and bearing stress. Previously, we discussed axial stress. So these two are just another type of direct stress. Let's start with shear stress. So shear stress is caused when the forces applied to an object are parallel to the object's cross-section. We have two types. We have your direct shear, which is caused by forces parallel to the sectional area, and then the induced shear caused by normal loads acting on inclined surfaces. So induced shear is something we already discussed within your actual stress topic. Okay. This is the shear that is present, or rather, this is the stress that is present whenever we have a normal force acting on an inclined area, as you can see by the definition. And we already know the equation for that. Now, because of this shear stress, the applied loads cause one section of a body to slide past its adjacent section. So that is the effect of shear loads on your body. And that shear load causes sliding, hence shear stress. Okay? So the major difference between normal stress and shear stress is that normal stress is perpendicular to the area, while shear stress is parallel to that area. For further discussion, we have three types of stress commonly found in structures. First is your single shear in rivet, double shear in bolt, and then shear in metal sheet produced by punch. Let me try to draw what that means. Okay, so this is your single shear in rivet. Okay, so we have two laps or two plates, and then one force on the left and another force on the right, as you can see by its cross section. Now, try to imagine when this happens, okay, this part of your rivet is the one that's experiencing your shear force, right? Because this top part is sliding to the left, this bottom part is sliding to the right, okay? And therefore, this area, this portion of your area, also experiences your shear force or shear stress. And then we have another free body diagram isolating only the top portion. As you can see, this bottom half or this bottom portion experiences a shear force, also known as your shear force V. Okay, so V equals P as per free body diagram. Now for part B, it's your double shear in bolt. So we have this ball, okay, we have this section with a force downward, and then this portion being pulled upward. Okay, again, try to imagine when that happens, this area or this portion of your structure or object slides downward, these two slides upward. So therefore, these two areas are the ones experiencing your shear stress or shear force. Isolating only this bottom part, as you can see, we have your shear force V. By the way, V means your shear force, explained further later. And then this force is divided into two areas because two areas are the ones experiencing that force. That's why this is P over 2 and P over 2. And then this is your P. Okay? These are just your free body diagrams. And then lastly, shear in metal sheet produced by a punch. So let's say we have this cylinder right here, then we have a metal sheet. Because of a force, this cylinder will create a hole in your metal sheet. Okay? Say we have this. Creates this hole. And then the area that's experiencing the shear stress is the perimeter of the hole because, okay, this portion of your metal sheet will slide downward while this portion of your metal sheet will remain stationary. Okay, so therefore the perimeter of this hole, as you can see here, the perimeter is the one experiencing shear stress. And V equals P, shear force equals your applied force. Okay, So P are your applied force, V is your shear force experienced by your area. All right? Okay. Next. So by that logic, we can have now our equation, shear stress represented by tau equals V over A, where V again is your shear force and A is your shear area. So recall our past equations. We have the general equation for stress. Okay, force over area. We have normal stress, P over A, where P is the perpendicular force to area A. And then now we have shear force tau equals V over A. Okay, so they're basically the same thing. They just denote different types of stress. So theta normal, tau shear, P perpendicular force, V parallel force. Okay? The next type of stress is your bearing stress. So bearing stress is the pressure caused by surface loads between two bodies pressed against each other. For example, the soil pressure beneath a pier experiences bearing stress, and the contact pressure between a rivet and the side of its hole. So we already talked about a rivet, right? We have a shear stress from a rivet, and another stress that it's experiencing is bearing stress. We'll illustrate that later. Now, because of this bearing stress, we have what we call a bearing plate. So bearing plates are used to distribute contact forces over a larger area to reduce bearing stress. Because if the bearing stress is large enough, it can crush a material. That's why we need something to distribute that stress so that the total bearing stress being experienced per area is reduced. So here's an example. We have your steel column. We have a base plate, also known as your bearing plate, and we have a concrete footing. Okay, this base plate, or again bearing plate, distributes the force carried by this column towards your footing. That's basic design of footing. Now, if we remove this base plate, imagine what will happen. Okay, area now will be concentrated on the cross-sectional area, or the area in contact between your column and your concrete footing. And that's a very thin area. What could happen is this concrete column, this steel column, could punch through the concrete footing, creating failure. Okay, because the pressure is distributed over a very small area. Right. So to further imagine what happens, try to imagine a paper horizontally suspended in air. Okay, take a pencil and try to punch through or apply a vertical force through your paper. Okay, doing that is easy. You can punch through your paper easily, right? Now, try placing a piece of cardboard, a square piece of cardboard over that paper, and try punching through or applying pressure on the cardboard towards the paper. It's not that easy to punch through anymore because the force from your pencil is distributed by your cardboard. Okay, so same thing happens here, distributes the force. Another example again is your bearing, is your rivet. So example A is rivet in your lap joint. And then in part B, it shows the actual bearing stress diagram. And then in part C, it shows the assumed uniform bearing stress on projected area. Let's talk about part A first. We already know from previous slides that this force P on either side, opposite directions, creates a shear force here. Okay? But once again, another stress that it creates is bearing stress. Now, in actual, this is how the bearing stress will look like. Okay? The bearing stress in a rivet is not constant. It's zero at the side of the hole, meaning on the other side, where it's not experiencing pressure, and then it's maximum behind your rivet. For example, here, okay, if this plate is pulled towards this direction, maximum bearing stress will be felt here, and then there would be a space here. Therefore, your rivet will not experience any shear there. For example, if we have this lap joint, right? This is your hole. This is pushed here, okay? Your bolt will look like this. So this is the maximum shear bearing stress. As you can see, it will create space here. That's why it's 0 bearing stress on that area. But it is common practice to assume that the bearing stress is uniform anyway, or uniformly distributed about a projected area, as you can see in part C. So this is the diagram that we're actually using in solving for problems, all right? So we have your hole there. Okay, the actual area, again, is half the perimeter, or rather the contact area between your rivet and your lap joint. That's the actual area experiencing bearing stress. But again, we're not going to use that. We're going to use a projected area. So to do that, okay, imagine your hole, right? Your hole is circular, and then it has uniform thickness. So that's basically a cylinder. Okay, you have your cylinder. If you look at this from the front, it looks like a rectangle, and that is the projected area that we need. So this cylinder being projected as a rectangle. So now the bearing area, or the area carrying the bearing stress, is assumed to be the thickness of the plate multiplied by the diameter of your rivet, or diameter of your hole rather. Okay, once again, we're not following this, even though this is the actual thing that's happening. We're going to use this assumption in our solution. Okay, projected area. Now the equation, again, it's similar to our general equation. Sigma equals P over A. Here, it's sigma sub B for bearing stress equals P sub B, which is your bearing force, over A sub B, which is your projected area. And as we discussed earlier, projected area is just the thickness of your plate, or the height of your hole, multiplied by the diameter of your hole, or diameter of rivet. Okay, so force, bearing force, over diameter of rivet times thickness of your plate. That's our equation. Any questions so far? Please answer in the chat before we move on to examples. Okay, great. Let's move on to example number 1. Let me just fix my setting. Okay, once again, number 1, I'm going to solve it on my own. And then number 2, I'm going to take recitation. So just follow along for now. Number 1, the lap joint shown in the figure is fastened by 4 rivets of 3/4 inches diameter. Find the maximum load P that can be applied if the working stresses are 14 ksi for shear in the rivet and 18 ksi for bearing in the plate. Assume that the applied load is distributed evenly among the 4 rivets and neglect friction between the plates. So basically, you're looking for maximum force, P. And then we're given restrictions, your working stresses for shear and bearing. So first step, write the given. Okay. First of all, we're given diameter of your rivets. So D equals 3/4 inches, right? And then as you can see, thickness of the plate is also given. We can write that as well, 7/8 of an inch. Then we're given working stresses. First is your shear stress, 14 ksi, and then bearing stress, 18 ksi. And then bearing. Okay, so that's all of our given. Now to solve for this, okay, we're gonna check for both shear and bearing stress. Okay. So let's start with checking for shear stress first. Recall the equation. Shear equals B over A. Okay. Shear stress is limited to 14 KSI. By the way, make sure your units are uniform. KSI just means 1,000 pounds per square inch, right? Kips, if you learned this in your MEC 30, kips is just 1,000 pounds. Therefore, KSI is just 1,000 pounds per square inch. 1,000 PSI. Okay, so 14. Next, V. V is what we're looking for. This V is actually the shear stress or shear force being experienced by each of this rivet. And recall the cross-sectional area of your rivet, right? This is where it experiences your shear stress. Okay? If we try to draw that in your figure, yeah, this is where it experiences shear stress. So there's 4 of that. So there's 4 areas. Okay. So therefore, that is P over 4 times the area experiencing shear. Okay, let's draw that properly. Once again, you have your bolt, cross section, no bolt. Let's do that 2D. So this is the 2D representation. Okay. Okay. Once again, this is your shear stress. Area experiencing shear stress. And that area is a circle, right? If you look at this 3D, that area is a circle. So this is 4 times the area of a circle, which is pi over 4d squared. Area circle. Pi over 4d squared or pi r squared. We're given diameter, so we're using pi over 4d squared. So 4 times pi over 4. Diameter is 3/4 inch. D squared. Make sure again your units are consistent. So inches, KSI again is 1,000 pounds per square inch. So uniform unit. Therefore, this is allowed. Okay. And then if I compute for this, we should get 24.74. And then how do we compute or how do we get the unit? This is KSI. So the force of that is kips. Okay, since we didn't convert anything, force is in kips. Okay, so that's just one option. This is the maximum load this lap joint can carry if only considering shear. Now let's consider bearing. Okay, and then our equation for bearing is PB over AB. Okay, so that's 18 KSI. And that what is PB? So bearing stress again, if you draw a free body diagram, as shown earlier, this PB is just equal to this force P. Okay, and then over area. Once again, we have 4 areas experiencing your bearing stress. So 4 times area of each. So projected area is what we need. Recall how to get the projected area. This. Okay. So this is our projected area. That is a rectangle or a square. And then the dimensions of that are shown in the drawing. Okay. Explaining this. So this base is equal to the diameter of the rivet, right? So base, diameter of the rivet is 3/4 times height. This height is the thickness of your plate, which is 7/8. So times 7/8. That's the area of each, that's the projected area of each rivet. And again, there's 4 of them, so times 4. So solving for this, you should get 47.25 kips. Once again, that's just an option. Now we need to analyze, once again, what's the maximum load P that can be applied. As I've mentioned in the previous meeting, okay, if you're a bit confused, the maximum force is always the least amount in your answer. So in this case, it's 24.74. Okay, so therefore, maximum force is 24.74 kips. Okay, if you want to properly analyze this, okay, you can say that, once again, this is the maximum load this can carry considering shear stress. This is the maximum load this can carry considering bearing stress, meaning if we apply this load, your structure or this system will fail under shear stress, okay, because this exceeds the maximum it can handle according to shear stress, okay? So that's why we choose the least amount, 24.74, okay? So that's number 1. Any questions for number 1? Please answer in the chat. Okay, great. Once again, if you're wondering why B is equal to P, PB is equal to P, it's because if you draw your free body diagram, that's how it's going to look like. For example, here, okay, this P is also equal to this P, right? PB equals P. You can see, only for these types of problems, okay? Again, this is done by using free body diagram. And the same for your rivet. And it's the same as our example. As you can see, if you draw the free body diagram, this is your P, this is your V, and then summation of forces X, V equals P. Now let's move on to number 2. Number 2, what force is required to punch a 20mm diameter hole in a plate that is 25mm thick? The shear strength is 350 meganewton per meter squared. Okay, so now we're looking for, again, force to punch a hole with a certain diameter. And our limitation is shear strength 350 meganewton per meter squared. So first thing, again, is write your given. We're given 20mm diameter hole. That's what we want. Okay. Number 2. So diameter 20 millimeters. What else is given? A plate that is 25 millimeters thick. So T, 25 millimeters, and the next shear strength is 350. So that's tau. 350 meganewton per meter squared. And remember, meganewton per meter squared is the same as MPa, which is Newton per millimeter squared. All right, so let's try to draw this, okay? Basically, this is what we want, okay? And then we want a hole. Okay. We want a hole punched through this plate. Right. Therefore, if we try so we want to punch this out. Let's write the dimensions. This thickness is 25 millimeters. And then this diameter is 20 millimeters. Okay, so my drawing's not up to scale. This is just to show you what's happening. One. All right. Going back, again, we're looking for force to create that hole, considering this is our limitation. Okay, so to solve for that, let's use the limitation. Once again, tau is equal to V over A. Okay, and this V will be the force that we need to create this hole. So typically, we're going to get a cylinder with the same dimension, then use that cylinder, pushing a force on that cylinder and on this hole. Okay, and then this hole has the strength, shear stress of 350 MPa. That's why we're still using that as our equation. And then based on this, the shear force that this hole will experience is equal to the applied force that we need. Okay? So once again, this tau is 350, and then this V is equal to your applied force P. Okay? Let's include that in the drawing. Once again, we're gonna need a cylinder with the same dimension to create that hole. There's gonna be an applied force P. And then this will have a reaction for shear force V. That's why P equals V. And then area. So this is the area experiencing your shear force or your shear stress, right? Can anybody give me the equation for that area? Okay, in case you don't know, this area is just the perimeter of this circle, right? Multiplied by this thickness. Very good, Tim. Dragon. 2 pi RH. Looking for equation. So, Dragon. 2 pi RH. Why? Recall. Once again, we're gonna recall. Perimeter of circle. That's 2 pi r, right? 2 pi r. Or pi d. Okay? And then we multiply the perimeter of your circle by this thickness to get the area experiencing shear stress, right? That's why we don't have r, we have d. So we're going to use pi d multiplied by this thickness, which is p. Okay, let's sub in our values. 350 equals p. That's what we're looking for. Pi diameter is 20. Once again, make sure your units are uniform. This is MPa, which is Newton per millimeter squared. Our dimensions are in millimeter, so it's uniform. Okay, even though this is meter, another way to write that is Newton per millimeter. So the millimeter will cancel out. This is pi. Okay, pi. D is 20. Thickness is 25. Once again, we're looking for P. Please solve. What's P? Okay, very good, Edwin and Trinity. It's 549,778.71. So Mira and Lavo. Okay, so 549,778.71. Unit is Newton. Okay, we take our unit from the stress, that's Newton. Or you can also go through the cancellation of signs. This is 350 Newton per millimeter squared. This is millimeter and times millimeter. So millimeter squared will cancel out. You're left with Newton. Or just memorize. Making sure your units are consistent. Whatever the unit of force and your stress is, that will be the unit of force of your answer. So this is the answer to number 2. Any questions for number 2? Please answer in the chat. How about the others? Please answer as well if you have any questions. Okay, no questions. Let's move on to number 3. So number 3 is a bit similar to number 2. So 3, as shown in the figure, a hole is to be punched out of a plate having a shearing strength of 40 KSI. The compressive stress in the punch is limited to 50 ksi. Letter A, compute the maximum thickness of plate in which a hole of 2.5 inches in diameter can be punched. And then letter B, if the plate is 0.25 inches thick, determine the diameter of the smallest hole that can be punched. So basically, we're given again limitations for the stress in the plate, and then we also have an additional limitation for the compressive stress in your punch. And then what we're looking for are dimensions. Okay, so let's, again, first step is to write the given. First, shearing strength 40 ksi. So that's tau 40 ksi. Next, compressive stress, that's sigma 50 ksi. What else? So for part A, we need the maximum thickness to punch a hole of 2.5 inches in diameter. So for letter A, diameter of hole is 2.5 inches. And then for letter B, if the plate is 0.25 inch thick, you want to look for the diameter. So plate thick, so thickness is 0.25. Okay. So we have two limitations, one for compression, one for shear. So what's happening here is this punch carries this force P. Okay, and then because of this creates a hole on your plate. Okay. But again, unlike our previous drawing, this punch doesn't have any limitation. So that's why we directly solve for shear. Okay, whatever force P is on your punch, that is what is being experienced, or that is the shear force of your hole or your plate. But now it's different. We have a limitation on that. So we're gonna start with that. Okay. So letter A, we're starting with the compressive stress. Recall the equation for compressive stress is P over A. It's your normal stress, right? And then stress is 50. This P is the maximum force that we can use in order to punch this hole. So that's one of the things we're looking for. And then what is the area? This area, again, is for compression. So take note, this area is the one perpendicular to your force. So can anybody give me the equation of this area? No, equation, not value. What's the equation of the area of the punch for compression? Okay, very good, Sophia. Beatrice. 1/4 pi r squared. It's the area of a circle. It's okay. Right? Because again, normal stress, force over area, and area is the perpendicular area. This is a circle, as you can see by the shape. So we're looking for the area of a circle, which is pi over 4d squared, or pi r squared. We're not given radius, we're given diameter. Pi over 4d squared. And what is that diameter? That d is given as the diameter of the hole. As mentioned earlier, the diameter of the hole is the same as the diameter of this cylinder. So we're going to use that as well. So finally, 50 is just equal to P over pi over 4. What's D? 2.5 inch. Make sure your units are consistent. This is KSI, 1,000 pounds per square inch. This is inch, so yes, it's uniform. 2.5 squared. Please solve for P. What's the answer? Correct. Laika and Trinity. Oh, blah, blah. 245.44. That's 0.44. Now again, ideally, try to store this in your calculator because we're going to use this again in the next equation. Now that I have P, I can now use my shear stress. Now we're moving on to the whole. Okay? So shear stress equals V over A. That shear stress is equal to 40 equals V. And that V, as mentioned earlier, whatever this P is also the same as the shear force being experienced by the hole. So V is equal to P, and then the area, and this is your P, area was the shear area. Okay? Compression area is different from the shear area. Can anybody give me the equation for the area experiencing shear? Sige, let's draw 3D again. Correct, Sierra. Okay. Yeah. Okay. Once again, this is the whole. Okay, this is the area, again, experiencing shear. This is experiencing shear. And then let's also include this. Yes, V equals tau A is another equation for this. Okay. Now this is the area experiencing compression. Sorry. So that's why this is the area of a circle, right? That's why our area here is pi over 4d squared. Now for shear, okay, this is the area. So that's why it's pi dt. So correct against shear. Gutierrez. pi dt, pi d being the perimeter of your circle multiplied by the thickness of your plate. So pi dt, okay, so 40 equals p using this over pi. What are we looking for part A? Compute the maximum thickness. So thickness is what we're looking for. D is given 2.5. So pi times 2.5 times t. From this, we can compute t. Please solve. What's the answer? Correct, Audrey and Jade. So 0.78. So Manrique, Lomito. 0.78. Unit inches. Inches. So that's the answer for part A. Now let's do part B. Okay. So for part B, what we're looking for now is diameter. Previously, we're given thickness, looking for diameter. Now we're looking for diameter given thickness, 0.25. Okay. So B 0.25. So same thing applies. We're still looking for the maximum force, but now we're not given diameter. So same equation, stress equals P over A. So stress is still 50. P is the same. Okay. And now the area is also pi over 4 d squared. The problem is there's no more value for P. So instead, our equation will look like this. P is now equal to 50 times pi over 4 d squared. Since again, we're not given d, we can't solve for p. Instead, we have an equation for p. Okay? And then moving on, you can now use your shear, which is tau. So tau equals v over a. Tau once again is 40. V is equal to p. So I'm going to use this equation, which is 50 times pi over 4 d squared over area. Area is the same, it's still this. So that's still pi d times thickness. So pi d, thickness is given 0.25. Okay, from this equation, please solve for d. What's the answer? Inches. Okay, correct. Rika, Bianya, and Julia. It's 0.8. So Solomon and Bianya. 0.8 or 0.80 inches. So that's the answer for part B. Okay, that's how you answer. Any questions for number 3? Please answer in the chat. Okay, great. Let's move on to number 4. Okay, number 4. Find the smallest diameter Find the smallest diameter bolt that can be used in the clevis shown in the figure. If P equals 400 kilonewtons, the shearing strength of the bolt is 300 MPa. Right. Once again, write your given. So first, this P is equal to 400 kilonewton. Next, what else? Shear stress. Shear strength and shear stress are the same. Shear stress just means the actual stress experienced by your object. Shearing strength is the same as the maximum stress it can withstand and strength. Okay, so shearing strength, maximum allowable shearing stress, working shearing stress, they all mean the same thing. That's your limit. So shearing strength is 300 MPa, so that's still your tau. And what are we looking for? Smallest diameter that will not exceed this stress. Okay, so we're looking for D. Once again, since this is what we're given, that is what we'll work with. So tau equals V over A. Tau being 300 MPa, once again, that's Newton per millimeter squared. Keep that in mind. So 300. Our force is in kilonewton. Okay, 400. So we need to convert that into Newton. So 400 times 10 raised to 3. Yeah, raised to 3. Converting Newton to kilonewton. Kilonewton to Newton. And then how about the area? Now make sure to analyze the given drawing carefully because, as explained earlier, make sure to count or to identify which areas are experiencing your stress. In this case, you already mentioned it previously, if you have a clevis or a bolt, the areas that are experiencing stress are these. Okay? Those are the areas experiencing stress. And that is the area of a cross-section of a bolt. Cross-section of a bolt is also a circle. Therefore, that's the area of a circle. It's 2. There's 2 of them, so that's twice area of a circle, which is 2 pi r. D is what we're looking for, so we're going to use the equation pi b. So pi over 4d squared, or pi r squared. Again, we're looking for d, so we're going to use the equation of area pi over 4 d squared. Okay, and then from this, we can solve for d. Please solve. What's the answer? Correct, it's 29.13 millimeter. Correct, John and Audrey. Paragua and Mabike. Okay, 29.13. Okay, and then unit, millimeter. Since once again, this is Newton per millimeter, we converted kilonewton to Newton. So Newton will cancel out. We're gonna be left with millimeter. Okay, so that is number 4. Any questions for number 4? Please answer in the chat. Okay, no questions. Let's move on to number 5. And we'll make this the last question for today. Number 5, a 200 millimeter diameter pulley is prevented from rotating relative to a 60 millimeter diameter shaft by a 70 millimeter long key, as shown in the figure. If a torque T equals 2.2 kilonewton meter is applied to the shaft, determine the width B if the allowable shearing stress in the key is 60 MPa. Okay, so let's analyze. So we have a pulley. This is your pulley. It has a 200 millimeter diameter. Okay, and then we have a shaft of 60 millimeters. So this is your shaft, and this has a diameter of 60 millimeters. Okay, and then we have a key, and this is your key, which is 70 millimeters long. Okay, also it's 10 millimeters high according to the drawing. Now this pulley is being subject to a torque of 2.2 kilonewton, or rather the shaft is experiencing 2.2 kilonewton meter torque. So now we have this key. This key stops, and this is your key. Looking here, that key stops the rotation. Okay. So now we need to know what is the allowable width of this key so that it won't break or it won't exceed its shearing stress. We need to figure out the dimensions in order to fulfill the requirement that we're not exceeding this shearing stress 60 and we're carrying this 2.2 kilonewton meter torque. Right? Let's do that. First step again is writing your given. So we have a torque. That's capital T, 2.2 kilonewton meter. We also have torque, which is tau, 60 MPa. Okay. So first of all, let's analyze what's happening. We have this key right here. We have to determine what kind of stress is it experiencing. We already have a clue. Since we're given your shearing stress, most likely this key is experiencing shear stress. Okay? More specifically, it's gonna experience shear here. Why? Because this shaft is rotating. Okay? The tendency of the shaft is to move this way. Okay? Because of that, it's gonna create shear here. Because the tendency of this key is to stay put, right? To stay non-moving. And then we have this area moving. Okay, remember, there's shear whenever there's two sliding objects opposite to each other. So now we know that there's shear there. Next step, what's creating that shear? Once again, the thing that's creating the shear is this movement. Okay, the circular movement of your shaft, which is torque. Okay, so now we have to know specifically what force is this portion experiencing because of that torque. Okay, to better analyze, let me draw a front view of that. Pixels. There. Okay. This is your shaft. And then we have a key. Let's choose a color for key. Blue. Yeah. we have this key. Okay. And then this is in motion. This is your torque. And then the area experiencing shear is this. Okay. So that's your shear plane. And then this is your 3D, so it's easier to see. Now we have to know what's creating that. Can anybody remember what's the equation for torque? Okay, can you give me what's the equation for torque from your previous classes? Correct, Tim. It's FD. Or, okay, more specifically, it's radius times. Very good, Julia. It's hard. Okay. Torque T equals FD or equals R times F, where R is the distance between your point of application to your axis. Okay, in the case that the one experiencing torque has a length, or in this case, okay, this is radius of your cylinder or radius of your area multiplied by force. And actually, this force is the tangential force. Okay. Tangential force. This is your F. Okay. So torque, yan, R, this is the radius. And then F is the tangential force from your torque. Therefore, that F is the shear force being experienced by this area. Okay? Well, now let's create our equation. So torque equals RF. Torque is 2.2 kilonewton meter. Radius of your, again, the one experiencing torque is the shaft. The diameter of your shaft is 60 millimeters, so that's 30. Now we need to convert, because our units are not uniform. This is kilonewton meter. This is millimeter. So to convert this into millimeter times 100, or sorry, times 1000. Times 100. Times 100, converting meter to millimeter. No, 1000. Meter to millimeter, 1000, right? Okay. That equals R. So now we can use millimeter. 60 is the diameter to get the radius divided by 2. So 60 over 2. And then F is what we're looking for. Please solve what's F. 73.33. Very good. Laika and Beatrice. So Daog Pascual. What's the unit of this? Anyone? What's the unit? Good, it's kilonewton. Why? Because we didn't convert kilonewtons yet. So correct, John and Fres, Krishaline, Paraguay. 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 Yeah. It's kilonewton. Okay, once again, this 1000 is just to convert meters to millimeters. So therefore, the final unit is still kilonewton. Kilonewton. But our stress is MPa. That's Newton per millimeter squared. So converting this to newtons just times 1000. So that's 7333.33 newtons. 33. 3. Newton. And then, as usual, store that. And that F is equal to your shear force. Okay, now we have your shear force. We can now use the equation for shear stress, V over 8. Shear stress is limited to 60. Shear force is this, right? That's your V. And then area, the area of your shear stress is this, right? It's also equal to this. It's basically a rectangle. This curvature is too small to be significant. Therefore, you can just consider this as a straight line. Okay. Therefore, it's this multiplied by its length, right? To get the area of the rectangle here. So base is equal to the thickness of this key, which is actually what we're looking for. So base times, now what's the length of our key? Given 70 millimeters. Okay, so check again your units. 60 Newton per millimeter squared. V is in Newton. 70 is in millimeter. Everything consistent. Therefore, I can now solve for V. Please solve considering V is equal to this. What's the answer? Very good. It is 17.46. So Krishaline and Sam for detail and please. 17. If you use the stored function of this or stored value, you should get 46. And then unit, millimeter. Okay? That is the answer to number 5. Okay? So in case, let me also include well, we get the area. Suppose we have this. Okay. Okay. Mm-hmm. Okay. Now indicate this is the shear area, which is a rectangle. This is B. This is 70. Okay. That's why that's the equation. Okay. Once again, any questions for number 5? Please answer in the chat. Okay. No questions. Next question is number 6. And the solution of this is a bit long. That's why I'm going to leave this for next meeting so that I don't have to rush through it. Okay, so I'm going to end the discussion here. Okay, and then So this is where we'll end shear and bearing stress. So before I dismiss you, we have a few announcements. On Saturday, you're going to have your seat work number 1. Your seat work number 1 will be available from 12:01 a.m. and the deadline or soft deadline for this is 12 midnight. Okay? There won't be any Zoom meeting on Saturday, as mentioned in our course orientation. Therefore, you may answer that whenever you want on your own time. You may answer it during our class lecture or class time. But once again, there's no Zoom meeting. Okay? So I will meet you next week, Tuesday. Another thing, your seat work is individual. Okay? However, you can still ask your classmates for help. I don't mind. But the purpose of the seat work is for you to practice and study the previous lectures. Okay, so please try to solve it first on your own. And then if you're having trouble, you may now ask your friends or classmates for help. If you do decide to just copy the answers, I urge you to please at least study and understand the solution, okay? So that you're prepared for the next quiz. I'm going to show you where your seat work will be shown. Okay, let's wait for it to load. So typically, your seat work will be seen here in week 2. You don't see it yet because I haven't included anything in it yet. I'm gonna upload it again on Saturday. So just wait, in the future, you'll see this week 2 and upload it there. So the way that you'll answer it is the same as your diagnostic exam. There's an assessment, multiple choice, there's answer. However, now you are required to submit your solution. Okay? Deadline of solution is also 11:59 p.m. on Saturday. Now, in the event that you're not able to answer your seat work, you still have a week to answer it. Okay? You don't have to message me about it. You don't have to send me an excuse letter. You can just answer it on your own time. However, remember, we have a maximum score of 70% for late submissions. Okay? Once again, all of these are mentioned in our Zoom recording, orientation course introduction, as well as here. You can also look at lectures, PDF file for orientation and course introduction. Okay? Do you have any questions, clarifications for me? Please ask now. None. I'm gonna end the Zoom recording.